So this steam engine works on the principle of heat engine, that is Carnot's heat engine. So if it come to know the types of heat engine, that is internal combustion engine and external combustion engine, we can say that the heat engine provides a continuous supply of work because it is a cyclical and the original conditions are maintained. Okay, there are two main types of heat engine. Okay, those are internal combustion engine and external combustion engine. Okay, so after that, first point is Carnot's heat engine. Okay, so this is Carnot's heat engine. So here Carnot's heat engines. It is first point. It is an ideal engine invented by Sadi Carnot. Okay, pronounce it Carnot. Okay, not Carnot. Okay, pronounce it Carnot. Second, it operates on the reversible cycle. If you remember the conditions and the working of reversible cycle, according to chapter number 3, heat and thermodynamics, you will come to know that this Carnot's heat engine works or operates on the reversible cycle. Okay, it means the initial conditions and the final conditions of the working substance are same. Okay, so this is the basic condition of reversible cycle. Then third one, it is free from all imperfections like friction and heat loss, etc. Since it is a ideal heat engine, okay. Therefore, it is free from all imperfections like frictions and heat loss, etc. So, this Carnot's heat engine has following parts. First one is the source. Okay, this source is having infinite capacity of radiating heat energy, and the capacity is measured in terms of Q1. Okay, it is maintained at a temperature T1. Okay, so T1 stands for temperature of source and Q1 stands for capacity of source. Okay, that is heat capacity of the source. It has got infinite capacity to radiate heat energy. Okay, say for example, if we think of sun, okay, the sun is the source for the solar system which radiates energy. Okay, so here source is maintained at temperature T1 having infinite capacity of radiating energy, that is heat energy Q1. So therefore infinite capacity of supplying heat, that is source. Second one, if source is there, then obviously in case of heat engine, sink must be there. Therefore, second part is sink. Okay, so sink is infinite capacity. Sink is having infinite capacity to absorb heat, and that capacity is Q2. Okay, and due to that capacity, the temperature of sink is T2. Okay, that is the T1 is the temperature of source and T2 is the temperature of sink. Okay, so here in the bracket HT I have written. HT means obviously it is high temperature, and in case of sink LT means obviously it is low temperature. And as I told you earlier, sink has infinite capacity to absorb heat. Okay, so whatever heat is supplied by the source is to be absorbed by the sink. Okay, so this is the general course. Okay, third one, insulating stand. Insulating stand is used to carry out adiabatic changes in the working substance. Okay, so simple points are mentioned on this slide, that insulating stand, it is used to carry out adiabatic changes. Next, working substance. Working substance performs mechanical work. Ideal gas is used as a working substance. Okay, in this case of Carnot heat engine, note that this Carnot heat engine is ideal engine. Okay, it is not used practically. It is an ideal engine. Therefore, it is free from all imperfections. Okay, therefore, therefore, it has ideal gas as the working substance. Okay, and the last part of the Carnot's heat engine is the cylinder. Okay, the cylinder has walls perfectly non-conducting, but the bottom is perfectly conducting. Walls of the cylinder are perfectly non-conducting, but the bottom of the cylinder is perfectly conducting. Okay, so note that the difference between the wall and the bottom of the cylinder. The bottom is perfectly conducting. Bottom of the cylinder is perfectly conducting. It is fitted with frictionless, weightless, and non-conducting piston. Okay. Next, the heat capacity of cylinder and piston is zero. Okay. Why this is zero? The heat capacity of cylinder and piston is zero, because if heat capacity is zero, then and then only this heat engine can prevent heat loss. Okay, only the bottom can absorb or reject heat. Okay, so let us deal one by one. Let us deal one by one means let us discuss first one, source, then sink, then insulating stand, then working substance, and last the cylinder. Okay, so suppose we have a source as indicated in diagram 1. Okay, so this is, suppose this is source is kept at T1 temperature, that is it is maintained at T1 temperature, and Q1 is the supplying capacity, that is heat supplying capacity of the source. Okay, so it has infinite capacity to supply heat. Suppose whatever working substance is there somewhere here, the working substance absorbs the heat. Okay, and due to absorption of heat, expansion of working substance occurs, and due to expansion, the piston moves in the upward direction as shown in the diagram. Okay, then after expansion, so this much is the expansion. After expansion, if the cylinder is kept on stand Y, that is on another stand, to carry out adiabatic changes. Okay, so here this is the insulating stand. Third one is the insulating stand. It is as shown in second diagram. That is the stand Y is the insulating stand, and here the T1 and T2, that is temperature of sink or lower temperature, and temperature of source or higher temperature, both are reversible. Okay, so after certain interval, if we keep the cylinder on this third one, that is on sink, that is on stand Z, and if you press the piston in the downward direction, then we can observe that whatever heat is absorbed by the working substance when it was kept on source X, the same amount of heat is released or rejected to sink. Okay, and the amount of rejected heat is equal to Q2, and the next temperature is equal to T3. So this is the working of Carnot's heat engine. After that, suppose we have this much diagram. Okay, that is in terms of cylinder, then source, then insulating stand, then sink, then piston, and certain adiabatic changes and isothermal changes, whether it is adiabatic expansion or compression, and adiabatic expansion and compression. These are the things which are to be discussed according to this slide. Okay, so after that, suppose we have studied the changes of the working substance when the working substance absorbs or rejects heat. Okay, so as I told you earlier, that this Carnot heat engine works on the principle of reversible cycle. Okay, so say for example here A is indicated or number 1 is indicated. Okay, then from A we shall start from A, then we shall move towards B, that is second point, then towards 3, that is C, then 4, fourth point. Okay, and once again we shall reach to the original position. Okay, so here If we observe the course of the working substance from A, B, C, D, and again A, okay, then we can say that this is the reversible cycle. Say for example, from A to B, if we observe the increase in the volume, okay, from A to B, here volume is present on the x-axis, okay, and pressure is present on the y-axis. Therefore, if A, that is the thermodynamic parameter of working substance, is A, that is initial conditions, that is in terms of pressure P1, volume V1, and temperature, whatever it is. Okay, so if A, that is a working substance, is traveling or going from A to B, the process is isothermal process. Isothermal process is the process where temperature of the working substance or a system remains constant. Okay. So after that, at B or at second point, T1 is equal to T2 is equal to TH, that is the higher temperature. Then the working substance goes from second to third position, that is second adiabatic. Okay. Second adiabatic means here, if we observe from A to B, we can observe that the expansion of the working substance has taken place. Expansion means, suppose if we extrapolate this point A on x-axis, we can reach to E. Okay, so E is the initial condition, and here 2 means F. So here you can observe that there is an increase in the volume of the working substance isothermally. Okay, so therefore increase in the volume is there, that is isothermal expansion process is there. Therefore I can, or we can identify the process A to B of the working substance as isothermal expansion. Okay, after that from B to C, again we can observe that this working substance has got little bit expansion. Okay, obviously expansion means change in or increase in the volume, more correctly increase in the volume. So as you observe the difference between F and G on the x-axis or volume axis, you can observe that this is the adiabatic expansion, okay, or sudden expansion of the working substance. So from A to B, isothermal expansion, and B to C, adiabatic expansion. That is the second process. Okay. So after C, that is at C, we can have T3 is equal to T4 is equal to T1. Okay. So after 3, suppose certain amount of heat, whatever is there, certain amount of heat, that is Q in, that is input heat energy, is absorbed by the working substance over here. Okay, and due to this absorption of heat, that is the isothermal expansion and adiabatic expansion, now the working substance is ready to reject the heat whatever absorbed. Okay, so from 3 to D, we can observe that there is change in the direction, okay, of the process, whether it is isothermal or adiabatic. If we are talking about C to D or 3 to 4, we can observe that from 3 to 4 or from C to D, there is decrease in the volume of the working substance. Okay, so decrease in the volume of the working substance means some or certain amount of pressure is applied on the working substance at constant temperature. Therefore, the third process is nothing but the isothermal compression process. Therefore, I shall write here isothermal COMP. So that COMP stands for compression. And after that, 4 to 1 or D to A, once again we can observe that this working substance has compressed to reach the initial conditions equal to A. Okay, so D to A is again decrease in the volume of the working substance from H to E. Okay, so the fourth one, that is the fourth process, is the compression process. Therefore, if it is sudden or fast, and if it has decrease in volume, therefore it should be referred as fourth state or process, that is adiabatic compression process. So overall we have four processes. First one is the isothermal expansion, second one is the adiabatic expansion, then isothermal compression and adiabatic compression. So overall we have two expansions, okay, and two compressions simply. So first expansion is isothermal expansion, second expansion is adiabatic expansion, then the reverse manner, that is isothermal compression and the adiabatic compression. Okay, so this is the indicator diagram or pressure and volume relationships of the Carnot's cycle. Okay, so after that, suppose we want to discuss the process A to B in terms of thermodynamics of the system. Okay, so here first one is the isothermal expansion process, the same which I have discussed with you in this slide. Okay, the same is stated over here, starting with the working substance represented by state A. Okay, that is P1 V1 on the indicator diagram. The cylinder is placed on the source X. Okay, the working substance absorbs heat from the source and expands. It is allowed to absorb heat, that is Q1, at temperature T1 Kelvin. Okay, this K, capital K, stands for Kelvin. That is the unit of the temperature of the source, and expand isothermally at the same temperature. Isothermally means same temperature, T1 Kelvin, to reach the state shown by B, that is P2 V2 on the PV diagram, pressure volume diagram. Okay, this process is represented by the isothermal AB. This is A and this is B, that is the isothermal expansion. And the work done in the process by the working substance is, now remember our third chapter, that is the expression for isothermal expansion. I have written over here, that is W1 is equal to nRT1 log to the base E V2 divided by V1. This is for area ABFE on the indicator diagram. So for area A, then B, then this is F, and then E. Okay, so for ABFE we have first process, that is the isothermal expansion. So this is equation number 1. Okay, after that, second process as indicated on the indicator diagram, that is we have to discuss from B to C or 2 to 3. Okay, so second process is the adiabatic expansion process, that is sudden change, that is sudden increase in the volume of the working substance. Therefore, the cylinder is then placed on the insulating stand Y. It then becomes insulated and hence no heat enters or leaves it. Okay, therefore adiabatic expansion of the working substance takes place. Adiabatic expansion means sudden expansion or fast expansion. It is allowed to continue until the temperature of the working substance falls to T2 Kelvin. Okay, if you remember, T2 Kelvin is the lower temperature of the sink. Okay, and reaches the state shown by C, P3 V3 on the PV, or it is also known as indicator diagram. The process is represented by the adiabatic BC, and the work done in this process of the working substance is W2 is equal to N into R divided by 1 minus gamma T1 minus T2. T1 is the higher temperature and T2 is the lower temperature. This is discussed for area BCGF in equation 2. Okay, so where is BCGF? So this is B, then this is C, then this is G, and then F. Okay, so for this much region, second process is there, that is adiabatic expansion process. Now the third one, that is isothermal compression process. Okay, so in case of isothermal compression, this is compression, not expansion. So in case of isothermal compression process, the cylinder is placed on the sink Z at temperature T2 Kelvin, and the pressure on the piston is slightly increased, and the work is done on the working substance. Okay, hence volume is reduced. Note that whenever reduction in volume of the working substance is occurred, then work is to be done. Okay, work is to be done on the working substance. Therefore, so due to this work done, that is due to compression, whatever heat generated due to compression is there, that is transferred to the sink, and therefore no change in temperature occurs. So this isothermal compression is continued until the working process reaches the state shown by C, P4, V4, and the process is represented by the isothermal CD on the indicator diagram, and therefore the work done in the process on the working substance is this Q2. Earlier we have discussed about Q1 in case of first process, that is isothermal expansion process. So here Q2 is equal to W3 is equal to nRT2 log to the base E V4 upon V3. This is for area CGHD, equation number 3. Where is CGHD? So this is C, okay, then this is G, then this is H and D. Okay, so whatever area is there, for this area isothermal compression is discussed. And the last one is the adiabatic compression. Okay, that is fast compression. Now in the last process, the cylinder is now placed again on the insulating stand Y, and adiabatic compression is made by increasing the pressure until the working substance reaches its initial state, that is A, and the change is represented by the adiabatic dA on the indicator diagram, and the work done in the process on the working substance is W4 is equal to NR divided by 1 minus gamma. T1 minus T2 is equal to area DHEA, equation number 4. So where is DHEA? So this is D, then this is H, E, and A. Okay, so for that much area, that is DHEA, equation number 4, that is adiabatic compression, work done in case of adiabatic compression. So therefore, if we combinedly discuss about processes, adiabatic compression, isothermal compression, then adiabatic expansion and isothermal expansion in the reverse manner. Okay, that is 4 3 2 1 or 1 2 3 4, whatever it is. This is the reversible cycle. Okay, thus if we talk about 1 2 3 4 or W1 W2 W3 and W4, or in terms of Q1 and Q2, okay, or in terms of T1 and T2, or in terms of the work done by the working substance. Okay, the cycle according to indicator diagram, the cycle A, B, C, D and A, okay, collectively ABCDA is thus completed. It is called Carnot's cycle. Okay, and the definition of Carnot cycle is, it is the reversible cycle of operation through which the working substance had been taken place. Okay, this is called as Carnot's cycle. It is the reversible cycle of operation through which the working substance had been taken. Okay, is called as Carnot's cycle. So this is the discussion about the Carnot's cycle. Okay, so please wait for a minute. So after that, After the discussion of this Carnot cycle, okay, this is a very wordy discussion. Okay, so for your simplicity, I have a video, okay, on YouTube, and I'm going to play that video so that you will understand how Carnot's heat engine works. Okay, so please be with us. I shall share the video with you.
So what are the things that we need to know about this life-changing cycle? So first, well, it is an ideal heat engine cycle by a French physicist, Sadi Carnot. It utilizes heat energy transferring from a heat source to a heat sink. In addition, it composed of four reversible processes. The reversible process means direction can be returned to its original position. Also, it uses ideal gas as its working medium. And note that this is a perfect engine. No friction between piston and cylinder walls, and no heat transfer between the surroundings and your system is considered. Now let's discuss how this interesting cycle works by exploring its processes, the four reversible processes. So now for the first process, process 1 to 2. This process is called isothermal expansion. Isothermal in thermodynamics means no change in temperature, or in other words, temperature is constant or not changing within this process. So what happens here is that the heat energy from the heat source is transferred into the ideal gas. As a result, the gas expands, which then increases the volume and decreasing the pressure. Now next, process 2 to 3, which is called an adiabatic expansion. Adiabatic in thermodynamics means that there is no heat transfer between surroundings and your system, or to put simply, all change in temperature is contained within a system, which as a result making the entropy zero. On this process, our volume increases and pressure decreases. Third process is the isothermal compression. So by compression, it means volume is decreased and as a result, pressure increases. On this process, heat energy from the gas is transferred into the heat sink. And finally, the last process. The last process is called the adiabatic compression. Since it's an adiabatic, all change in temperature is contained within a system, and our entropy is zero. Also, since this is compression, it means our volume decreases while our pressure increases. So that's it. That makes it a cycle. So now let me ask you this. Why Carnot cycle is the most efficient cycle? Mhm. Well, it's because Carnot cycle is a perfect engine. The processes are reversible, working medium is an ideal gas, and of course, the thermal capacity of heat source and heat sink is infinite, which makes no reduction to both during heat transfer, as we have observed, right? But for all those same reasons, it makes this cycle impossible to operate in our real world, as obviously those things don't exist. Well, of course, we should not forget that it contributed so much today. In fact, it is a model of our car engines like Otto and diesel cycle. And so that's it. Once again, this is Easy Engineering. See you again for our other easy and fun engineering topics. Is engineering topics made easy and fun for you.
So, okay, have you understood how the Carnot cycle is working with the help of this video? Then the same process, that is the Carnot heat engine, how it works, that is from process number 1, 2, 3, 4 and again to 1 we have discussed, okay, on the slides, and it is according to the YouTube video. Okay, so after that we have to calculate the efficiency of Carnot heat engine, that we shall discuss afterwards. Okay, but before that, if you have any doubts or queries regarding the Carnot heat engine, you can ask me. Okay, and before that, today we have discussed Carnot's cycle. Carnot's cycle, okay. Then its indicator diagram, or it is simply Carnot's cycle or pressure volume diagram, okay. Then isothermal expansion process, adiabatic expansion process, the second one, that is W2. Here is W1, then W2. Then third one, isothermal compression process, that is Q2 is equal to W3. Then adiabatic compression, the fourth one, that is W4. Okay, so if you remember these four equations according to our work done in adiabatic process and work done is work done in isothermal process, okay, according to our thermodynamics chapter. Okay, so here if you remember, W1, W2, W3 and W4, only four equations, we can able to calculate the efficiency of the Carnot heat engine. So what is efficiency? According to our earlier concepts of HSC, efficiency means output divided by input. So here, what is output? This is Q2, and what is input? Q1. Okay, so here is input, Q1 is the input, and this Q out is the output. So if we take a ratio of output divided by input, we can calculate efficiency eta of the Carnot cycle. It is very simple. So in the next lecture we shall discuss this one. So therefore I insist you to remember W1, this one, then W2, then W3 and W4, which are useful for the calculation of eta, that is efficiency of the Carnot cycle. Okay, so with this we shall stop over here, but don't go. I have to make an announcement.